Hi, in this video, we want to take a look at R squared when we have fixed predictor values, and then we're going to take an initial look at generalized least squares. All right, so when we're talking about sum of squares error, we can write that in this format. So sum of squares error is equal to the sum of square deviation of y from y bar minus the centered x transpose times y, and then I've got the centered x slope estimates there. All right, well, I can rearrange these terms like this. And here, that's sum of squares total, right? All right, let's write that as SST. And, this is, by rearrange terms, I've got SSC. Over here, we're going to call this sum of squares regression. Okay. So we'll go ahead and remember that the beta 1 hat is the centered version of x estimate of the slope. So remember that we are making our reference point the x bar vector y bar instead of you going through like the 0 vector. Okay, well, if this is the situation I have, all right, here is how I estimate the slope. Well, I can multiply both sides by x transpose c, x sub c, and then I get this equation. All right, well, if I look at this, if I multiply both sides by beta 1 hat transpose, then I can see that I've got this term up here, my sum of squares regression. So sum of squares regression is this, and by doing a little bit of multiplication with this estimate equation, I get that on the right. So I know that sum of squares regression is equal to this right here. Well, okay, let's go ahead and let's rewrite this as centered x times its estimates of the slopes transpose centered x times beta 1 hat. Okay, all right. So that's just another way to write sum of squares regression. So the coefficient of determination, let's go ahead and say that that is r squared, and this is going to be the sum of squares regression over sum of squares total. Now, if we think about this equation here, sum of squares total is equal to sum of squares regression plus sum of squares error, and all these terms are positive, then sum of squares total has to be greater than or equal to both of these, right? It has to work out that way. So we know that this fraction has to be between 0 and 1 because it's positive, and sum of squares regression has to be less than sum of squares total. Okay. Well, I can take this and I could just rewrite things in the manner. So I'm going to replace sum of squares regression with this part here, put that in the numerator. Sum of squares total, I'm going to write it in the usual manner. Now, if we remember, I can rewrite this as, so sum of squares total is the same as y transpose y minus n times y bar squared. Okay, well, what I'm going to do, I'm going to, inside here, so ignore that little thing, I meant to erase it off. I can add and subtract, regular beta hat transpose x transpose y. I can add and subtract that in between here. And I can look at this and I can realize that this is another way to write sum of squares error and sum of squares regression. All right, so if I take this part here, this is my sum of squares regression because this is the formula for sum of squares error. So what we've done, we've gone and we showed that this is sum of squares total. We know that this is sum of squares error, and we know that we have this equation. Therefore, this has to be equal to sum of squares regression. Nicely. Okay. Well, let's go ahead and use this to rewrite r squared. Okay. Let's do that. So I've got beta hat transpose x transpose y minus n y bar squared, coming from this representation of sum of squares regression. And here I have a formula that we already established as y transpose y minus n y bar squared is my sum of squares total. All right, so why this is nice is that we can see it's, it's easier to compare these two. So the difference from r squared to 1 comes from the difference between beta hat transpose x transpose y and y transpose y. So the difference between x, beta hat, and y is the difference that arises between x squared and 1. Now, something to realize is that if x was random, then R would be estimating a population multiple correlation. But here in our situation for now, we're talking about x being fixed constants. They're known values. Okay, well, let's look at some properties of R squared and R. And at this point, we've looked at the, we've grown up with this concept. So this should not be shocking to us, but we'll go ahead and repeat this. All right, so, from the argument that I gave a moment ago, R squared is between 0 and 1. Now, if beta hat sub I is equal to 0 for all I greater than 0, so here everything except for the y-intercept, then R squared has to be equal to 0. And also, if sum of squares error is equal to 0, then from the equation with sum of squares total, sum of squares regression, sum of squares error, we know that R squared has to equal 1. Nice. All right, so we can use a different notation. We can say that R is the correlation between Y and modeled Y. So it's a correlation between Y and modeled Y that we get from our multiple linear regression. So R is equal to the correlation between Y and the fitted values of the model. Now, something that is interesting is that adding a variable to a model cannot decrease R squared. So it's either going to stay the same or it's going to increase. Now, it's going to stay the same when there's 0 covariance between the target variable and the new predictor, but the vast majority of the time it'll increase, even if it's very tiny. Now, if my slope is equal to 0, and now here this is population slope. So if the population slope is 0 for all I greater than 0, so here we're saying that the slope for all the predictors truly is 0, then the expected value of R squared is k over n minus 1. Okay. Now, in general, R squared cannot be partitioned into like k components. So if I have k predictor variables, I can't break up all the aspects of the correlation that's going on between the fitted values and the target variable. But if the columns of x are mutually orthogonal, then we can get R squared to be partitioned out, and I can figure out what portion of the correlation is coming from each predictor variable. And so in this situation, we're saying that the covariance between predictor variables is equal to 0 whenever the predictor variables are not the same. Now, R squared is invariant under full rank transformations of x, and R squared is invariant to scale transforms of y, but it's not invariant to scale transforms involving x and y. And so this invariant transformations for x is a big deal. This is one of the reasons why we can use so many different transformations on our data when we're doing stuff like machine learning and linear regression. All right, so if you think about that expected value, when all the slopes were equal to 0, if k is proportionally large compared to n, so I have a lot of predictor variables compared to my sample size, then a large R squared is meaningless. Really, there's not really a whole lot going on there. And the regression model, therefore, is also meaningless. So if I go back up here, I'm going to scroll up. If I look at this, so if I'm in a situation where the slope of all the predictor variables is truly actually 0, then I'm going to have expected value of R squared is k over n minus 1. All right, well, if k is pretty close to n minus 1, then you know what? So like if I'm in a situation where I see that I've got R squared close to k over n minus 1 and k is large compared to n, then really I can't trust my model. My model is really meaningless. All right, well, so something about R squared, if I keep on throwing predictor variables in and in and in without worrying about other aspects of like overfitting, then r squared has to increase. Okay, so we know that from our mathematical analysis, if I have something that is increasing and it's bounded by above, it has to converge. All right, so if I keep on throwing in variable after variable after variable, I can get a really good looking r squared when in fact I just have crap for a model. Okay, so what we want to do, we want to adjust our r squared calculation so that it's a more meaningful situation. So here's what we're going to do. Here's my game plan. I'm going to take r squared, but I'm going to subtract off the expected value when I have like zero slope. So I'm going to take r squared, I'm going to subtract k over n minus 1. All right, that's this parenthesis right here. Now, if I go through and I look at this version of r squared is going to be biased. It's going to be small. It's going to be too small. So what we're going to do, we're going to go ahead and we're going to make an adjustment. And we're going to multiply by the right values to make it so that adjusted r squared is no longer biased. Okay, let's do that. All right, and that's going to end up being multiply the numerator by n minus 1 and divide by n minus 1 minus k. Okay, so now let's go ahead and rearrange the terms with it. So just do a little bit of intermediate algebra. And I can see it's n minus 1 times r squared. I've got an n minus 1 here. I've got k and I've got k. All right, so this gives me a representation that this can like help me understand the difference between adjusted r squared and r squared. So something that is important, our adjusted r squared will always be smaller than r squared. And one thing I like to do if I see a big difference between the two, I know between adjusted r squared and r squared, then I know that I need to be worried about overfitting my model. All right, so let's go ahead and I want to write r squared in terms of sample variances and sample covariances. And I would like to do this using matrix formulas. All right, so I'm going to go ahead and use my sum of squares regression over sum of squares total formulas here. All right, well, it works out. If I was to go through and work out the details of this, this is covariance y with x transpose, and then the inverse of the x covariance matrix, n minus 1, inverse of the sample x covariance matrix, then S times, covariance matrix of y with x. Okay, well, if I look at this, I know it's going to end up being this guy right here. Okay. So now let's think about the geometry of correlation for a moment. So this is something that I feel needs to be better understood in the statistics community. Okay, so I'm going to take us back to Calc 3 just for a moment. And we're going to talk about the relationship between dot products and angles. All right, so recall that if I take any two vectors from linear algebra, matrix algebra, or Calc 3, that U transpose V is equal to the norm of U, norm of V, cosine of the angle between the two vectors. Standard formula. Okay, so what we're going to do, so remember the dot product is equal to the norm of the two vectors times cosine of the vector of the angle between the vectors. All right, so here's what I'm going to do. I'm going to replace U with y minus y bar. I'm going to replace V with modeled y minus y bar. And I'm just going to go through and I'm going to plug and chug. Okay, so when I take the dot product on the left and over here, I'm going to put y minus y bar times the j vector here. I'm going to put fitted y minus y bar j in here. And I'm going to leave cosine theta. I'm just going to say theta is the angle between the vectors. Okay, well, I know that it's a 2 norm. So I know that that's the sum of squared observations. Then take the square roots. And I represent that with this matrix formula. And same thing for the V. And then this is just the dot product formula. Okay, so I want to get cosine by itself because I want to talk about geometry right now. All right, so I divide both sides by the square roots, gives me this, okay. Now, a little bit of side work. If I go through if I take this part of the numerator, I add and subtract the fitted values, I can go ahead and distribute through. Now I realize that y hat, so sorry, y minus y hat will always be perpendicular to the predictor variables used to fit y hat. All right, y minus y hat is perpendicular, it's orthogonal to all of the columns used to fit y hat. Okay, so if I think about that for a moment, y hat is the output of those columns, okay? And then J is the y-intercept column and corresponds to it. So I know that this has to be orthogonal to y hat and it's orthogonal to J. Therefore, this has to be equal to 0. Therefore, this business is just equal to that. All right, well, hold on a second. That looks kind of familiar. That is this part here is the same as this part here. Oh, there should be a transpose on that right there. Okay. All right, well, then I have this divided by its square root, or so I have what's here is in the numerator, and it's being divided by its square root. Therefore, it simplifies down to that. Okay. So now I'll go ahead and rewrite the square root. Well, I recognize that this is sum of squares regression. That's sum of squares total. There should be a transpose right there. And so this is the square root of r squared. All right, this is good. This is interesting. Okay, so now we're going to go ahead and just say that cosine of theta is equal to r for this. Okay. Now, let's think about cosine for a moment. Well, cosine of 0 is 1. Remember that cosine is adjacent over hypothesis. When I talk about the Cartesian coordinate plane, x, y, and the radius, so or the hypotenuse, then cosine is x over r. On the unit circle, cosine is like the x value on the unit circle. Okay, okay. So angle 0 gives me 1. Pi over 6 gives me approximately 0.87. Angle pi over 4, 45 degrees, is about 0.7. Pi over 3 is about half. And then angle pi over 2 gives me cosine of 0 because that's vertical. Okay, well, let's think about something. If I have a correlation that is less than 0.7, I have a correlation less than 0.7. Think about the angle. Or if I'm talking about correlation of 0.7, then approximately the angle between the vectors is 45 degrees. If the correlation is less than 0.7, then the angle between the vectors is greater than 45 degrees. It's between 45 degrees and pi over 2. Well, pi over 2 is perpendicular, right? So if I see a correlation less than 0.7, then my observed values and my modeled values are closer to perpendicular than parallel. Okay, now think about that for a moment. In geometry, we say that parallel is like the model of being informative to something else. Like two vectors are more informative to each other if they're parallel. And if they're perpendicular to each other, they are independent of each other. Knowing like where I am along one vector's direction tells me nothing about the other one if they're perpendicular to each other. Okay, so anytime I see an r squared less than 0.5, y and y hat are closer to perpendicular than parallel. So that means that if I see an r that in magnitude is less than 0.7, or if I see an r squared less than 0.5, really the vectors are closer to independent of each other than, or I should say covariance of 0. They are closer to covariance of 0 than they are of being perfect correlation. So this is something to be mindful of. So whenever you read a paper, and my experience is this has been usually with social sciences or with vendors trying to say that their product is statistically significant. I've gotten into some back and forths with people, with vendors over correlation, by the way. If you see a correlation that, an R that's less than 0.7 in magnitude, or you see an R squared less than 0.5, just know that really it can't be informative. Now, if you do hypothesis testing and I have 10 million data points and I see that, my R squared is statistically greater than 0 and my R squared is 0.48, something like that. Well, you know what? 0.48, even if it's statistically significantly greater than 0, that does not mean it's operationally significant. So whenever you interpret hypothesis testing and statistics, realize that there is statistical significance, which is all about like really sample size and our assumptions. And then there's operationally significant. If you see a correlation, an R squared less than 0.5, really that's operationally not informative for the vast majority of situations. The only time that 0.5 R squared would be useful would be when really we're in the situation where we don't have information otherwise, and this is the best that we can get. And usually in those situations, we're really not even going to be using data. We're going to be using subject matter knowledge and just people's personal beliefs rather than statistics to reach a conclusion. All right, so another way to write sum of squares regression over sum of squares total is the sum of square deviation between fitted values and the average of the target variable. And this one is one we know and love. Okay, so now let's take a look at generalized least squares. So remember, if I'm talking about regular old linear regression, multiple linear regression, or simple linear regression, we have an assumption that the covariance matrix for the residuals is equal to a constant times the identity. Okay, so there's a couple things that fall out from this. First and foremost, the variance for each residual is the same, and it does not depend on the x values. So the variance of our residuals given x is equal to the same for each of the residuals. Also, because the diagonal is 0 in this matrix, we're saying that the covariance between the residuals on observations is always equal to 0. And so if I'm talking, so I'm having like, assuming we have 0 standard deviation, which we will for this, we have 0 correlation. If I'm doing the normal model, then I get independence between residuals for free. Okay, so. All right, well, what if we're in the situation where this is not the covariance matrix of our residuals? Let's say instead, I have something like this, where we have the covariance is equal to a constant times a positive definite matrix. Then I cannot proceed using regular old least squares regression. I need to adjust things. So here are some common violations for the covariance of epsilon to be equal to a constant times the identity. So one common situation that we see is that the variance of our residuals increases as the x predictor variables increase, and we can see sequential observations are correlated with each other. So if I look at my residuals and I see something that looks like a time series plot, then I can go like, hey, I do not have covariance of 0 between my residuals. All right, so for generalized least squares, what we're going to do, my model is pretty much the same, but we're going to change it up. We are going to go ahead and instead of having the identity matrix inside the covariance aspect, we're going to have a known positive definite matrix. So y is equal to x times beta plus epsilon. Expected value of y is x times beta, or expected value of epsilon is equal to 0. Covariance of y is equal to sigma, which is little sigma squared times that known positive definite matrix. Okay. Now, in this situation, what we're going to do, we're going to go ahead and say that sigma squared is unknown, but V is known. All right, so V is a positive definite matrix. So V is symmetric. And V has n diagonal entries and n choose 2 distinct off diagonal entries. All right, so if we were to go into the situation where we treat V as an unknown matrix, then we have n plus n choose 2 unknowns. That means that we have more unknowns than we have of data points. If I have more unknowns than data points, I cannot use system of equations to solve it. I have to somehow use something else. I have to use some outside knowledge. I can't use equations to do this. So what we do is when we do a generalized least squares model, we have an idea of what the relationship between the residuals are, and then we proceed from there. So we have an assumed structure of that covariance matrix, and then we basically fit that as best we can. All right, that's all I've got for you. Take care and goodbye.